Can you see my PPT?
Yes, sir.
And my audio is clear now?
Yes, sir.
Okay. So now, from today, as we have discussed initially, there are 9 important points to be noted in this transport phenomena subject. So, whole transport phenomena subject will revolve around these 9 points, 9 parameters. So, initially we have correlated heat transfer, mass transfer, and momentum transfer, and then concluded these 9 parameters. These 9 parameters are viscosity, thermal conductivity, and diffusivity in molecular flux, and then interface flux, heat transfer coefficient, mass transfer coefficient, and friction factor. And then the property, basic property is velocity, temperature, and concentration. So we have already had a discussion. So how to get the value of thermal conductivity, viscosity, viscosity, and diffusivity. Then we had a discussion how to get the heat transfer coefficient, mass transfer coefficient, and friction factor. Now, from today onwards, so we'll be discussing how to get the profile for these properties, velocity, temperature, and concentration. That is what we are going to cover in a remaining part of transport phenomena. So, it needs some complex mathematics and basic definition also. So generalized definition for a discussion of this velocity profile. So whenever and whichever this complex mathematics is needed, that time I am discussing, I will be discussing this mathematics and basics from where whichever is needed information. So basically, so and don't get lost in this complex mathematics. Okay, this mathematics is just a tools to understand the physics of the problem that you need to understand. So you need to concentrate on physics also. If you get lost in mathematics, so many people will tell that transport phenomena is just mathematics. That is not the case. That is altogether wrong. So mathematics we are using to simplify the transport phenomena. That is what you need to understand. So we'll give attention to mathematics only the level which it needed. Okay, we'll not go in details of mathematics. So we'll stick to our physics of the problem and discuss this all derivation of velocity profile, concentration profile, and temperature profile. But certainly when we go for unsteady problem, turbulent problem, complex problem, that time mathematics will be dominating, and you slowly make up your mind that mathematics will also get involved in this subject slowly as we go down the line in this subject. So, we have discussed this Newton's law of viscosity. I think in second class itself we have discussed Newton's law of viscosity. So this is tau yx. So what we have discussed here? Here we have discussed laminar flow. There was a velocity only in x direction. There was a velocity only in x direction, and this velocity was varying or changing in y direction. So there is a flow in x direction. So there was x velocity, and this velocity is changing in y direction. If I move in my y direction, at certain point there was zero velocity. At certain point there was maximum velocity. So velocity was changing in y direction, and this is the Newton's law of viscosity we have discussed. Minus mu equals to dvx by dy. So this is very simple equation. When I want to generalize the equation, okay, generalize, get the velocity profile and all. So certainly this equation will not be useful, and this equation is kind of a you can say special case of generalized Newton's law of viscosity. So where only I have only one velocity, which is that one velocity? Only one velocity in x direction, and that is changing in y direction. But actually in natural and many of the chemical processes will not be so simple that you will get only one velocity and that is varying only in one direction. Okay, certainly you will have complex flow. So, and this is actually already we have discussed molecular momentum flux in y direction. Tau yx is a molecular momentum flux in y direction because of velocity in x direction. This is x momentum flowing in y direction. This is simply when I have only Vx. Vx, I have only Vx. Vy equals to 0, Vz equals to 0, and Vx is varying only in y direction. With respect to z, Vx is constant. With respect to x also, Vx is constant. Vx is not changing in x direction, Vx is not changing. So that time, this is the Newton's law of viscosity. This is the simplified form of Newton's generalized law of viscosity. So what do you mean by Newton's generalized law of viscosity, as I told? So this chemical processes is not so simple that I have, so what case we are discussing? I have only Vx and it is varying only in y direction. But you can have Vx in real life problem. You can have Vx, you can have Vy, you can have Vz. All three velocities you can have. Okay, and this Vx, Vy, Vz can change in x direction, y direction, z direction, and there can be unsteady problem also. So there should be some Newton's law of viscosity which will define all this variation and give all the stresses, all the momentum flux. So how many momentum flux component will be there? If I have this kind of thing, there will be 9 components. Okay, x momentum flowing in xyz direction, y momentum flowing in xyz direction, and z momentum flowing in xyz direction. So certainly there will be 9 component, 9 component of the flux here, and there will be viscosity is also. Viscosity is kind of a representation of molecular interaction. Molecular interaction depends upon, you can say, steady state, transient state. That also molecular interaction depends on. If I have multiple velocity, that will also have some effect on this molecular interaction. Certainly, so viscosity is kind of have a more detailed meaning, as we are discussing generalized just simple Newton's law of viscosity. So this, for that we must understand what is generalized Newton's law of viscosity. So deriving the generalized Newton's law of viscosity is not so easy. Okay, because of this, because I have all three velocities and all three velocities varying in x, y, z and time also. I can have unsteady flow also. I can have x variation in x, y, z, all three velocity. It is very complex. It took long time for mathematician to derive this equation, generalize Newton's law of viscosity. Just we'll have brief idea. So this is what you can say. This is what generalized Newton's law of viscosity is there. So there will be 9 components. Okay, tau ij. I varies from 1 to 3. I varies from 1 to 3, and this will be k and l. Okay, k and l. It is similar to this xyz Cartesian coordinate and velocity in xyz direction, similar to that only. Okay, so this there are 3 velocities and it is varying in all 3 direction along with time also, ij, k, l. So ij, k may be xyz. Okay, ij, k may be xyz and l will be time. So you can compare with this thing. So as such, there will be 81 component, 81 quantities which will represent a similar property to viscosity. Okay, so similar property to viscosity, and these are called as a viscosity coefficient. All these are viscosity coefficient. How many? There are 81 component. Okay, in Cartesian coordinate. So 81 components are there. Then they have applied so many assumptions and logical assumptions they have given. So we are handling most of the time fluid. Then so many assumptions are added and they have reduced this equation to this generalized form, where they have reduced down this 81 quantity to 2 quantities only. Okay, so it is very long discussion. Okay, long discussion, and maybe you will find this discussion in some of the fluid mechanics book, where these details are covered, generalized Newton's law of viscosity and its derivation. So huge mathematics is also involved, assumption and everything. So they have reduced first of all, and this is engineering important. Okay, mathematician will always target to use this equation with 81 viscosities, but slowly adding the assumption. So this, most of the engineering purpose is solved by using this equation, where delta ij is a chronicle delta. Okay, chronicle delta, and we are discussing variation of velocity in x direction, variation of velocity in y direction, variation of velocity in z direction. We have all three velocity, and this ijk varies from xyz actually. So, and steady state problem. So, and it is reduced down to only two viscosity component. Just for time being, you assume that it is not so easy, okay, to get the generalized Newton's law of viscosity. So this there will be 81 quantities, 81 viscosity coefficient after adding all the assumptions, and this is the most of the engineering purpose of the momentum transfer can be solved by using the generalized Newton's law of viscosity. And the generalized Newton's law of viscosity should be such that it should reduce to my original form. Okay, simple Newton's law of viscosity when Vx is varying only in x one direction. So it should, I should get that form from the generalized Newton's law of viscosity. So this is more than enough. This is more than enough. And what is coefficient A and B? This coefficient A and B, this is actually coefficient A and this is coefficient B. Okay, and this, it is written del dot V plus V, del V transpose. Okay, that is what I was telling, that we'll discuss some of the mathematics also. So same equation is there. Okay, this is same equation. Okay, same equation is written in compact mathematical form. So A equals to minus of mu. Okay, A equals to minus of mu, and B equals to 2 by 3 mu minus K. So both are viscosity coefficient. Okay, both mu and K are a viscosity coefficient. Both are viscosity coefficient, where mu is called as a viscosity, general viscosity, and K is a dilational viscosity. K is called as a dilational viscosity. We have physical significance to viscosity. Physical significance to viscosity. It is similar to viscosity. You can say another component of the viscosity while discussing generalized Newton's law of viscosity. But the nature of generalized Newton's law of viscosity is such a that, so you will never come across the dilational viscosity. So as far as chemical engineering is concerned, you will never come across this dilational viscosity. Okay, this viscosity coefficient you will never use. Why? Because if you are using gases, fluid as a gases, then the value of dilational viscosity coefficient is negligible as compared to mu. So you can neglect this. You can neglect this. So this will be very close to zero when I am treating gaseous flow. When I am considering liquid flow, this del dot V equals to zero. Incompressible. Liquids are incompressible. So this will be equals to zero. If for gases, this will be equals to zero. And for liquid, this will be equals to zero. So most of the time, the dilational viscosity will not have any role to play in most of the chemical engineering problem. But you should know there are 81 viscosity coefficient will come across, you will come across 81 coefficient, viscosity coefficient, when I am considering all velocity Vx, Vy, Vz, and it is varying in xyz, and as well as it is varying in time also, unsteady flow. So out of this 81, after adding all the assumption, people have reduced this. So people have reduced this equation so that only it can work with a two velocity coefficient. One is a viscosity, another one will be dilational viscosity. But for chemical engineering, you will never use this dilational viscosity. So you will never come across dilational viscosity anywhere, because either you will be handling gases or liquid. Okay, and for liquids, this so this will be a del dot V equals to zero. It is, this represent incompressible flow. So, and for gases, this will be equals to zero. That is why. So, and this actually del, now we'll discuss whatever mathematics is required. Del, it is called as a del operator. Okay. Del, it is called as a del operator. So, and mu is a viscosity, K is a dilational viscosity, and delta is a chronicle delta. So chronicle delta, what is the chronicle delta? It is a unit tensor with of component delta ij. If I am representing delta ij, delta V is a velocity gradient. So this is called as a del V. It can be pronounced as a del V, and this is a velocity gradient with a component del by del xi Vj. Okay. And transpose is a transpose of velocity gradient. This T, this looks like a plus sign. So you can remember it like a transpose. So it will be a transpose of velocity gradient. So it will be exactly reverse of this, this, and del dot V. This is called as the divergence of vector factor, velocity vector. Okay. Divergence. Del dot V. It is pronounced like del dot V, and it is called as a divergence. So hereafter, so you will be using this many a times. So slowly, as I told, I will be introducing you to mathematics which is needed and whenever it is needed. So don't get involved in much in this. Okay, you need to concentrate on physics of the problem also. So this is called as a gradient. So this can be pronounced as del V. This is del V. V stands for velocity. Del V or del into V. Not del into V. Del V itself you can say. Del into V is different thing, property that we will discuss whenever needed. This is del V transpose and this is del dot V. So this is a divergence of velocity, and this is the gradient of velocity. Okay, gradient of velocity, gradient tensor, and this is the divergence of velocity. So this is Newton's generalized law of viscosity. So now this property of del, it is similar to, for remembering, it is similar to a differential operator. Okay, it is similar to a differential operator. This is the definition of del. Okay, so what is the importance of this compact mathematics? So if you have this compact mathematics, you can remember, you can get back the equation in all Cartesian coordinate very easily if you remember what is the definition of del and how it is operated over V. So you need not to remember the equation in Cartesian coordinate, in equation in cylindrical coordinate, in equation in spherical coordinate system. Only you remember what is the definition of del operator and what is the operation over a property, which property. So this is del V. This is the definition of del in Cartesian coordinate system. So summation I del by del xi. Okay. So del 1, this is conical delta, which will have a value either unity or 0. So the property of conical delta will be, it will have value at specific condition 1, otherwise at everywhere else it is 0. So del 1 by del x1, del 2 by del x2, del 3 by del x3. Similarly, this is the definition of del operator for cylindrical coordinate system r, theta and z. And this is the definition of del operator for spherical coordinate system r, theta and phi. So now I know definition of del, and this how del into V, not del, how del V is operated. If I know, I can get back the generalized, and del dot V is operated. So I can get back the generalized Newton's law of viscosity for cylindrical coordinate system as well as spherical coordinate system. That is the importance of this compact representation of mathematics. So remembering this equation is very easy. So, and this property, once you remember, this will be same for everywhere. Definition of del and how del V is operated, del into V is operated, del dot P is operated. So what is the gradient, divergence? That maybe down the line we will discuss that also. What is gradient, what is divergence? Once you get familiarized with the use of this, then you will appreciate that why mathematics is important in transport phenomena also. That time we will have one class over details of this del operator and its operations. Okay, gradient, divergence and curl, that is called as a gradient. Del into V, gradient, del dot V is divergence and del into V is curl. So that we will discuss down the line after some time. Okay, so this is the definition of del operator. This is generalized Newton's law of viscosity. Now certainly, so del dot V is okay for Cartesian coordinate system. This is del dot V. How del dot V is operated for Cartesian coordinate system. So if you use this definition, substitute I j k equals to x y z. Okay, x y z I j k equals to xyz. So you will get del dot v equals to del vx by del x plus del vy by del y plus del vz by del z. This is how you can get divergence. Okay, mathematical operation. So now I have this property of del and del into, and this is how del v. Okay, del v is operated. Del v or del into v. Okay, del into v. This is also called as del into v or del v. Simply del v. So del v is gradient of velocity with respect to some coordinate. Okay, and transpose will be exactly reverse. And this is how a generalized operation of del v. Okay, generalized operation of del v, where ijk varies from xyz. Ijk equals to xyz. This is del v and this is del v transpose. It will be, you can say ij, and this will be ji. Okay, ji, ij, del xi, del j, vj, and del xj, vj, vi. Okay, so this is how gradient is operated. This is how this divergence is operated. This is the general operation divergence over a vector. Velocity is a vector. This is a gradient of a vector. Gradient of vector, how it is operated. Just for time being, you should remember this. This is how we are getting this compact nature, and using this compact nature, I can get back my main equation. Okay, so now this is important. Okay, this is, here I have del dot v. Okay, here I have del v, del vj by del xi, and here I have transpose of this. Okay, here I have transpose of this. Substituting all this mathematical operation in generalized Newton's law of viscosity, what I will get? I will get this minus mu dvj by del xi plus dvi by del xj plus 2 by 3 mu by k dvx by dx plus dvy by dy plus dvj by dj into delta ij. So this is what I will get, generalized Newton's law of viscosity, where this represent one viscosity coefficient which is equals to a, and this is represent another viscosity coefficient which is equals to b. Okay, so now what is tau yx equals to? So this is tau ij. Put I equals to y and j equals to x. So what will be tau yx equals to? It will be minus mu. Put I equals to y and j equals to x. Okay, I equals to y, j equals to x, I equals to y, j equals to x, and this will be as it is. And here tau delta xy. Okay, delta yx, not xy, delta yx. Okay, so this will be equals to minus mu d vi y by dx. Okay, so minus plus dvx by dy plus 2 by 3 mu k, and it is as it is. Okay, now delta is a chronicle delta. The property is such that it will be unity where I equals to j. I equals to j, it will be unity. Otherwise, it will be 0. Okay, for this case, so this will be 0 actually, because here I is not equals to j, so this equals to 0. That is one case where you will not get this second quantity. Another case is sometimes this for gases, this will be equals to 0, dilational viscosity, and for liquid, this whole bracket will be equals to 0. For incompressible fluid, the divergence of velocity will be equals to 0. For incompressible fluid, velocity will not change in x direction. Velocity will not, y velocity will not change in y direction, and z velocity will not change in z direction. So if you remember our first equation where I have only Vx velocity. I have only Vx velocity and it is varying only in y direction. So this will be 0. Now this is generalized Newton's law of viscosity, which is giving me x momentum flowing in y direction. Okay, this is generalized Newton's law of viscosity, which is giving me x momentum flowing in y direction. Okay, so x momentum flowing in y direction minus mu dvy by dx plus dvx by dy plus 2 by 3 mu minus k dvx by dx plus dvy by dy plus d. So first of all, I is not equals to j. So this equals to 0. As this equals to 0, this whole term equals to 0. This whole term equals to 0. Then I have only one velocity. There is no velocity in y direction. So this is also equals to 0. As this is equals to 0, tau yx equals to minus mu dvx by dy. This is what the equation is there. Okay. So as I is not equals to j, Kronecker delta. So this equals to 0. And moreover, so this I don't have velocity in y direction. I don't have velocity in y direction. So it will be reduced down to same equation. That is what we were studying a special case of Newton's generalized law of viscosity, where there was only one velocity and it was varying only in one direction. Okay, so this is Newton's generalized law of viscosity. So this is clear to everybody. Anybody has anything to discuss over this? So most of the time we'll start with this equation, Newton's generalized law of viscosity, for deriving the velocity profile, and then substitute appropriate this thing, or at least this. At least we will start with this. Okay, and then substitute the appropriate assumptions. One velocity, because as I told, for gaseous flow this will be equals to 0. And sometimes this will be equals to 0. For liquid, this bracket will be equals to 0. So most of the time this will be equals to 0. This second bracket is not important in most of the chemical engineering cases. Simple chemical engineering cases. When we go for complex problem, okay, complex problem and transient problem, that time maybe that is related. But as far as this basic transport phenomena goes, so this is not so important. This second bracket is not so important. So you should start with this and put appropriate assumption. And this is actually generalized Newton's law of viscosity. This is generalized, and both are called as the viscosity coefficient. This is dilational viscosity and this is actually viscosity. Both have same physical significance. Okay. Now, what is next? So molecular momentum flux. Okay, molecular momentum flux tau yx. Actually, it consists of two fluxes. One, this is what the viscous tau yx consists of two fluxes. One is a velocity gradient, whatever flux is happening because of velocity gradient. Another one is the pressure fluxes, actually pressure forces. So there are two momentum flux in molecular momentum flux. So this itself, okay, this tau yx is consist of two fluxes. Okay, this is molecular flux. There is no bulk motion at all. That is represented by molecular flux, and it consists of two fluxes. One will be a fluxes because of viscous forces, another will be a fluxes because of pressure forces. And this pressure forces fluxes will be only in a molecular momentum flux in a direction of flow. If molecular momentum flux is there in the direction of flow, that time this pressure forces play a role in the direction of flow. If you are discussing a molecular momentum flux in other direction, if direction is x and I am discussing y and z direction, that time only this viscous forces are playing a role. Okay, so for this, okay, so you just consider this cubical element in xyz direction, and just consider this point xyz. Okay, at xyz, this is x direction, this is y direction, this is z direction. This is the elemental volume of the fluid of delta x, delta y, delta z, and this is the center point of the fluid xyz. You draw a plane perpendicular to x direction. perpendicular to x direction. So tau x is a momentum flux in x direction. Okay, tau x represent momentum flux in x direction because of viscous forces. This is because of viscous forces. So P into delta x represent a momentum transport because of pressure fluxes. Okay, and this tau x will have three components. Tau x will have three components: tau xx, tau xy, tau xz. This is momentum flux in x direction. Okay, how momentum is flowing in x direction? It will have three components: tau xx, tau xy, tau xz. Okay, so this is tau x. This is how momentum is flowing in x direction. Indirectly, I am telling that this is the momentum flowing in x direction. That can be because of gradient of x velocity. So tau xx, it can be because of gradient of y velocity. It can be because of gradient of z velocity. So three component of x momentum will be tau xx, tau xy, and tau xz. But p into delta x, it will be only in a direction of x only. If flow direction is there in x direction, so it will get added up. Okay, this will be a pressure forces. So momentum flux because of pressure forces. Now this already we have discussed. Okay, if say velocity is there in y direction, how to physically interpret a momentum flux in x direction. So that we have discussed in second class itself. So molecules are moving because of interaction forces and all this. This will be there. Okay. Without bulk motion, momentum is transferred. So to understand this, how molecular momentum flux is taking place because of pressure forces. So you please look at this video, pendulum. Okay, it is very simple. The pendulum video. So where molecules are not moving, that pendulum is not moving, but momentum is transported. Momentum is transported. Just hold on. Can you see the screen, YouTube screen?
Yes, sir.
Okay. Just I am switching on this video. Can you see what is happening here? Just I am repeating same video. Okay. Again, I will repeat same video. Just observe video carefully what is happening. Okay. Again, once again, observe this video carefully. So now look at this. What is done at this stage? This first steel ball is taken at higher level and momentum is given to this steel ball. Some momentum is given to this steel ball and then it is left now. It is left. Okay, now you can see this momentum is transported to this steel ball. This momentum is transported to this steel ball. This momentum is transported to this steel ball. And this momentum is transported to this steel ball. So on same thing, this steel ball are not at all moving. There is a negligible bulk motion in this steel ball. So you can see this. You can see. Just observe this steel ball. There is negligible bulk motion. So what is happening? Momentum is transported in x direction, but there is no bulk motion. Okay, what is happening here? Momentum is transported in the direction, but there is no bulk motion. So only this molecule is moving. This molecule is not at all moving, and all momentum is transported from this place to this place. Okay, this is just an example. Now you can imagine on molecular level how to interpret this P into delta x. So one molecule is giving momentum to another molecule is giving momentum to third molecule, and momentum is transported because of the pressure forces. It is not viscous forces. Viscous forces, already we have discussed how momentum is transported because of viscous forces. Okay, because of velocity gradient, there will be intermolecular force of attraction. That is what viscosity is there. Because of that, a momentum is transported. That is a viscous forces. But here there is no viscous forces playing a role. One molecule is pushing to another molecule is pushing. This is push force. That is nothing but the pressure. So molecular momentum transported, that is because of the pressure fluxes. Okay. So there are three components of the x momentum: tau xx, tau xy, tau xz, and certainly this will have addition only in x direction. So delta x, this chronicle delta is added in such a way that delta x will have one value in x direction, unity value in x direction. All other values, it will be 0. In all other direction, it will be 0. So it will be added only to tau xx. So x momentum flowing in x direction. Okay, x momentum flowing in x direction. There only that pressure, momentum, flux, molecular moment. This is molecular momentum flux. It is not a convective momentum flux. This is the molecular momentum flux without bulk motion of the fluid. Okay. Similarly, I can consider y direction. Y direction, it will have three components, and z direction, it will have three components. So total molecular momentum flux. So till now we were concentrating only on this. Okay, molecular momentum flux because of viscous forces. Now today we have added this to discussion. Okay, because life is not so easy, because there will be some pressure forces also. Because of that only velocity gradient is playing a role. So when I am going to discuss all ij component, okay, tau ij, 9 component of the molecular momentum flux, this pressure force is also playing a role, because till now we were discussing I naught equals to j. That time this I naught equals to j, this will be equals to 0. Okay, this will be equals to 0. Hence, we are not discussed these pressure forces at any point of time. Now we are trying to generalize our discussion. I varies from xyz, j varies from xyz. So all these 9 component will be there. That time this will play a role. Okay, so this will be a total molecular momentum flux, and this will be a molecular momentum flux. Momentum flux is there without a bulk motion. Okay, momentum is transported. So as can be seen from this, so momentum is transported from this steel ball to this steel ball. There is no bulk motion in this steel ball. Okay, so you can see now. So there is no bulk motion. There are negligible bulk motion. So bulk motion is not at all very negligible bulk motion in this three steel ball. Still momentum is transported from this point to this point. So this pressure fluxes is nothing but the molecular momentum flux or conductive momentum flux. Conductive momentum flux, and that will be there only in a direction of one direction only. Okay, x direction when I equals to j. So forces in a direct j direction is unit area perpendicular in I direction. All this what we have discussed is there. So now there will be 9 component. I varies from xyz and j varies from xyz. Okay, so these are the three momentum. Okay, x momentum, y momentum, z momentum. Again, x momentum will have 3 component, y momentum will have 3 component, and z momentum will have 3 component. This is normal. So this will be a momentum in x direction. This is momentum in y direction. This is momentum in z direction. And it will have again 3 component. Okay, it will have 3 component. So these are the 9 component. So this pi xx is a total molecular momentum flux. Total molecular momentum flux. So this you can see I equals to x, j equals to x. So delta x will be equals to 1. So this will be equals to pressure plus tau xx. Now this is y component. okay, y component of x momentum. So delta xy equals to 0, hence pi xy equals to tau xy. Similarly, pi xz equals to tau xz. This will be tau yx equals to tau yx. This will be pi yy. So delta yy again equals to unity. This is the property of chronicle delta. So chronicle delta will have unity value in a given direction. Everywhere else it is 0. So when here when I equals to j, it will have value 1. Otherwise it will be equals to 0. So pi yy will be equals to p plus tau yy plus this will be a pi yz equals to tau yz, and this will be a tau zx equals to tau zx. Pi zy will be equals to tau zy, and this pi zz equals to p plus tau zz. And this is molecular momentum flux. All these are the 9 component of conductive momentum flux. Okay, conductive momentum flux, it consists of two components. One will be a conductive momentum flux because of pressure forces, which will be there in only three components when x equals to this and this. And this will be a conductive momentum flux because of viscous forces. So till now we were discussing only this, but now as we want to elaborate our discussion and want to use all these 9 components. So this is also important because till now what we are discussing only this. So it doesn't have pressure tau yx. There is a x velocity and it is varying only in y direction. Only we were discussing this. So hence we have not introduced this. But now as we want to discuss, we want to see the broader view of molecular momentum flux. It consists of two flux. Molecular momentum flux will consist of two components. One will be the molecular momentum flux because of viscous forces. Another will be molecular momentum flux because of pressure forces. Okay, and this pressure forces, it will be the part in only three. When delta I equals to j, it will play a role only in xx component, yy component, and zz component. And this is all molecular momentum flux. Still, we have not considered convective momentum flux. Okay. Anybody has anything to add here? This is just a elaboration, generalization of a discussion which we have discussed in second class, because there we were discussing only in one component, tau yx. We are discussing only how y momentum is flowing in y direction because of x velocity. How x momentum is flowing in y direction. Okay. Okay, so and you can see this is how it will be general representation. This is pi x, pi y, pi z. So momentum flowing in x direction, momentum flowing in y direction, momentum flowing in z direction. How it is represented? Delta x will be equals to 1 in x direction. Otherwise, it is equals to 0. Delta y equals to 1 in y direction, otherwise it will delta z equals to 1 in z direction, otherwise. So these are the 9 components. Now convective flux. So again we had a discussion about convective flux also. Convective flux
Hello,
will
sir.
be a, yeah.
Sir, there are few doubts in the chat box.
Yeah, tell me.
They
So
have
can
written
you
in
just
type.
tell me what are the doubts?
Yes, sir. The first doubt is from Abhineet. He's asking, is the generalized equation valid for laminar flow only, or
Yeah.
can
That is laminar flow is a special case of generalized equation.
or he's asking, or can it be applied on turbulent or transient flow as well?
It can be applied to any flow. Or laminar flow will be the special case of that generalized Newton's law of viscosity. Okay, so it can be applied to any flow, laminar, turbulent, transient, any flow it can be applied to.
Okay, sir.
Okay.
Next,
And whatever we have seen is a special case, laminar flow, and that to velocity varying in one direction. Okay.
Yes, sir. Abhinit,
Who
if
is
you want
asking
to
that?
add. Abhinit
Who
asked
is
that to
asking?
me.
Vinith. Vinith,
Yes,
na?
sir, Abhinit.
Let me see chat box. Abhinith. Yeah, roll number 116. Yeah, why del equals to 0 and not equals to, that is the definition of delta, chronicle delta operator actually. That is the mathematical operator which is used. Why it is non-zero and why it is zero, it is, I can't elaborate on this. It is the operator used when I needed such a property. It is called as a chronicle delta. Abhinit,
Yes, sir. Clear, sir.
clear, na? And then roll number 103. Tau XX, PX are different. Roll number 103, Saurabh,
Yes, sir.
can you just elaborate your doubt?
Yes, sir. Sir, like we learned, tau xy is the momentum in y direction due to the flow in x direction, right?
Just can you repeat? It was not clear. XY is
Sir,
a,
sir, we learned that tau yx is the momentum in y direction due to the flow in x direction.
no. It is X momentum flowing in Y direction.
Yes, sir. Sorry. And so, sir, tau xx is momentum flowing in x direction due to the flow in x direction, and
Yeah, and that too without bulk motion.
yeah, without bulk motion. And p right now we studied that that is also the flow momentum flux flowing in the x direction without bulk motion. So, sir,
Yeah,
how these both
Just,
are different?
I'll give you this is just consider imaginary case. Okay, you have series of molecule. Okay, series of molecule is there arranged in a row.
Yes, sir.
Series of molecule is arranged in a row, and somehow this first molecule start moving in x direction.
Okay.
First molecule start moving in x direction, and because of some interacting forces, certainly this some momentum will be given to second molecule also. Just,
Okay. Sir, it is hard to imagine.
I will pin. Okay. Now just consider this molecule, this molecule, this molecule, this molecule. This is line of molecule, and this is x direction. Okay. And now somehow you imagine that this molecule start moving in this direction. So it will have some Vx velocity. And now this molecule is connected to this molecule with some forces that is called as the viscous forces. This molecule will also have some velocity. Okay, this molecule will also have some velocity. This will be say Vx1. So Vx1. And why this is happening? This is just because there is some pulling force between these two molecules. That will be a tau xx.
Okay,
Because
sir.
x momentum is transported in x direction. Which direction it is transported? In x direction itself. This is x direction. I have x velocity. Previously we were discussing this. Okay, previously we were discussing this, and this molecule start moving in this direction. Because of interacting viscous forces, it will pull this molecule. Then it will pull this molecule. Similarly, now this first molecule start moving in x direction. It will pull second molecule, and the second molecule will pull third molecule. So this there is a momentum flux, momentum, this x momentum, because there is momentum in x direction, and this momentum is given to first molecule only. but it is transported in x direction because of viscous forces, that is tau xx.
Okay, sir.
Okay, and say now I am applying pressure here. I am applying pressure here. So momentum is given to this last molecule only. Okay, momentum is given to last molecule, and this momentum is flowing in x direction, and this first molecule start moving in x direction. That is what is happening in that pendulum case.
Yes,
and
sir.
that is this momentum flux.
Okay, sir. Got it.
Okay. Roll number 63, Shreyas. Yeah, delta. That already I told. This is a mathematical
Sir,
operator.
clear.
This is mathematical operator. It is called as the chronicle delta. It will have unity value in appropriate direction. Otherwise, it will be equal to 0. So, and it is introduced in a discussion so that now I want P here. P doesn't have any role to play here because this is X, Vx is there and P is there. Okay, if say this is P, so that P has a 0 component here. If I am discussing a momentum flux in y direction. Okay, this is momentum flux in y direction. That component of P in this y direction will be 0. So I don't want P here. I don't want P here. I don't want P here. So only in x, y, z direction perpendicular, there only P has a role to play. Okay, that is why this chronicle delta is introduced such a that now from this equation I can get back all these 9 components. Okay, from you can see what is the importance of mathematics from this equation. Okay, this is the compact form of this equation. This is compact form of this equation. So this is the molecular momentum flux. This is molecular momentum flux, and this molecular momentum flux. So this molecular momentum flux consists of molecular momentum flux because of pressure forces and molecular momentum flux because of viscous forces. Now I can get back all these 9 components. So first I will put I equals to x and j equals to x. So I will get this. Then P delta xx equals to 1. Then tau xx. Now I equals to x and j equals to y. So I will get this component pi xy, and now this delta xy equals to 0 and tau xy. So I can get these 9 components. So what is the importance of this compact mathematical operators and use of it? So you need not to remember all these 9 components. Okay, you need not to remember all these 9 components. You can remember only the short form of the equation where mathematical operators are used with suffix and prefix. And if you remember the definition of this mathematical operator and range of ij, so you can get back all these 9 components. That is the importance of mathematics in transport phenomena. Certainly, operating mathematical operator in compact form will be easier and you can easily operate mathematics over this compact form rather than all these 9 components. So I will do all mathematical operation over here. Okay, and certainly back of mind I know that okay I will have 9 components which I can obtain from this equation. I varies from 1 to 3, 1 to 3 or xyz or ijk. Sometimes it is called as ijk, sometimes it is called 1 to 3, sometimes it is called as xyz. J varies from same thing actually, xyz. Okay. Yeah, anybody else? Any confusion over here? This is generalized Newton's law of viscosity. Okay, now still this is the molecular momentum flux only. This is molecular momentum flux. Still we have not added a convective momentum flux. So what is convective momentum flux? Convective momentum flux is a quantity per unit volume into characteristic velocity. These also we have discussed So this is what convective momentum flux. So there are 9 components of convective momentum flux. Rho into V is a quantity per unit volume, and this is the characteristic velocity. And these are the 9 components of convective momentum flux. This is X component, this is Y component, and this is Z component. So it is rho V. So rho into V is a quantity per unit volume, or momentum per unit volume, multiplied by velocity. So if you want to recall, you can go back to all video recording and see quantity per unit volume and characteristic value. This velocity is integrated with the convective flux. Okay, so this represent, this is how x momentum flowing in x direction by convection. Okay, what is the meaning of this? How x momentum is flowing in x direction because of convection. Okay, how y momentum is flowing in x direction because of convection. How z momentum flowing in x direction because of convection. Okay, how this is x momentum flowing in y direction because of convection. Okay, so likewise there are 9 component rho vv. Okay, so this you can in compact form will be a rho vi vj. I varies from xyz and j varies from xyz. So this will be a total momentum flux. This will be a molecular momentum flux. Molecular momentum flux will be a summation of molecular momentum flux because of pressure forces, and this is molecular momentum flux because of viscous forces. And this is the total momentum flux, which will be a summation of molecular momentum flux, conductive momentum flux. So this and this is a conductive momentum flux, and this will be convective momentum flux, rho vi vj. So this is the total momentum flux. So for deriving the velocity profile equation, generalized velocity profile equation, so that we'll discuss. There are 2 ways. Either you can use simplified equation if you know your system very well. Otherwise, you start with the generalized equation and add one by one assumption. Add assumption one by one, and you will get a whatever with the simplified equation suitable for your case. So this is generalized equation of the flux, where everything is discussed. Pressure fluxes is discussed, convective fluxes is discussed, viscous fluxes is discussed in all the direction I, j, k. I can get in all these 3 direction. I varies from x, y, z, j varies from x, y, z, and that is what I can get 9 component of phi I, j. Okay. So just I will revise the PPT. So just give attention what is the content of this PPT. If you have any doubt on any PPT, so you can just let me know. Just give attention and just recall whatever discussed on corresponding PPT. So everything is fine. So with this brief discussion, now we can start methodology to how to get the velocity profile equation. For this, we are going to adopt a shell balance approach. So what is shell balance approach? There are multiple ways for you can say for writing a balance equation. So the mass balance you are well aware of. Similarly, you can do momentum balance also. Similarly, you can do a heat balance also. For doing these balances, there are many approaches. So for here in this transport phenomena subject, what we are going to adopt is a shell balance approach. So what is shell balance approach is? So we will consider a differential shell of a differential value delta x, delta y, delta z. Okay, that shell is considered, and we will take a momentum balance over this differential shell. First of all, we will apply momentum balance over this differential shell, and then we'll integrate this equation over a total boundary. And using boundary condition, we'll solve this integrated momentum balance equation. Okay. Solve using boundary condition, we'll solve this integrated momentum balance equation for momentum transfer to get the velocity profile. If you do a heat balance, you will get a temperature profile. To get a mass balance, you will get a concentration profile. That is what a shell balance is there. So mainly it is a differential shell which is integrated to get the velocity profile using boundary condition. That is what shell balance approach is there. So that is what we will discuss now. Shell balance approach. Okay. So this is the shell momentum balance equation. So how to get this momentum balance? So rate of momentum in. So here why we are discussing flux from so many classes. So you can see here also we have discussed flux. This is the total flux. Total flux consists of, this is molecular momentum flux and this is convective momentum flux. Why we are discussing flux? Because we will be reading fluxes to get the rate. To get the rate, we will be discussing flux. So flux information is very, very important. Okay, so how to get this rate, how to get the rate from flux? Here on number 23, Kaushik.
Hello.
Yeah, how to get the rate from flux? Kaushik?
Yes, sir. Yes, sir. Sir, like multiplying by area.
Very good, very good. It's simply some geometric input is needed, that is area, perpendicular surface area. So you can get a rate from flux. So this is overall shell momentum balance equation. So this is a convective rate of momentum coming in to my differential shell. Differential shell is nothing but the control volume of a differential diameter. So this is the rate of momentum going out by convective transport. Okay, this is convective momentum plus rate of convective momentum plus going out, rate at which momentum going out. This is molecular momentum flux coming in, rate of molecular momentum flux coming into my differential shell. This is the rate of molecular momentum flux going out plus forces of gravity acting on the system equals to 0. So if you remember mass balance equation, what is mass balance equation? Rate of mass coming in plus rate of mass going out plus rate of mass lost by consumption plus whatever be the rate of mass generated because of reaction plus accumulation. Okay, that accumulation, okay, equals to 0. So here for steady state accumulation equals to 0, and this is kind of generation and consumption of momentum. Okay, rate at which momentum is generated and consumed. This is this two bracket, this bracket and this bracket is representing the rate of momentum coming into my differential shell. This two bracket represent a rate of momentum going out back from the differential shell. This is also going out. This is also going out. This is generation and consumption of the rate of momentum. So this is because of generally because of gravity. Otherwise, some other forces also there. Pressure forces are there, which is considered in this momentum flux. Only remaining is gravity. Whatever be the momentum added or subtracted from a system because of gravity, that can be taken as a generation and consumption of momentum because of gravity. That is equals to 0. So accumulation we are taking 0. So accumulation of the momentum, that is we are taking 0. That is because here in this basic transport phenomena subject, we are handling only steady state. In steady state system is characterized by the zero accumulation. There will not be any accumulation. Accumulation term will be 0 in steady state. That is what the characteristic of steady state. So that is what equals to 0. So accumulation equals to 0. This is overall shell balance equation. Okay. So with the time when we will solve couple of problems, then you will understand how this can be interpreted as generation and consumption of a rate of momentum for a given differential shell. So this is rate of momentum coming in. This is the rate of momentum going out. And this is generation and consumption of the momentum, and accumulation equals to 0 for unsteady state problem. So we need to take this accumulation also. For solving transient problem, we need to take accumulation also. That is equals to 0. So overall, this is the shell momentum balance equation for steady state problem. So generalized method for shell momentum balance equation. So this is the generalized method for solving any shell momentum balance equation. Okay. So given a problem, so you select the coordinate system. This is first step. So select the coordinate system, then identify non-vanishing velocity component. So you study the system carefully and get the non-vanishing component of the velocity and the variable on which it depends upon. Whether I have all three velocity, whether it is varying in all three directions. Okay, and most of the time accumulation will be 0. So time variant will not be there. Then write a momentum balance equation. Write a momentum balance equation. Let the thickness of the shell approaches to 0. Okay. Then fourth step is let the thickness of the shell approaches to 0 and make the use of definition of first derivative to obtain the corresponding differential equation for momentum flux. Okay, let the thickness of shell approaches to 0 and make the use of definition of first derivative to obtain the corresponding differential equation. And this generalized method is true for shell momentum balance also, shell heat balance also, shell mass balance also. Only the thing is, this will be same. Here instead of discussing velocity, you will be discussing concentration, you will be discussing temperature. This step will be as it is, this step will be as it is. Then integrate the equation to get the momentum flux distribution. If you integrate this equation, so you will get a momentum flux distribution. Here differentiation, here integration. So you will get a momentum flux equation for a system. This equation was for a differential shell. When you integrate, sum it over, so you will get a momentum flux equation for a whole system. So insert Newton's law of viscosity. Then insert Newton's law of viscosity in momentum transfer. It will be Fourier law of heat conduction in heat transfer and Fick's law of diffusion in mass transfer. So obtain a differential equation. Obtain a differential equation. Then integrate this equation. Use appropriate boundary condition to get the velocity distribution. Now this is here itself you will have a differential equation in terms of velocity, or differential equation in terms of temperature, or differential equation in terms of concentration. So if you integrate this equation and use a boundary condition, so you will get a velocity distribution. So once you have velocity distribution, so you can do lot of calculations, lot of design calculation in momentum transfer. So you can use this velocity distribution to get other important quantities such as maximum velocity, average velocity, drag force on a surface, mass flow rate, volumetric flow rate. You can get lot of design important property in momentum transfer. This is what generalized method for shell balance we are going to adopt, and this generalized method is useful for momentum transfer also, for mass transfer also, for heat transfer also. Only the appropriately you need to extrapolate the information, similarity between all these three variables. Here I am discussing velocity. In heat transfer I will be discussing a temperature. So I cannot discuss velocity in temperature in x, y, z direction. That you should remember. Temperature is a scalar, velocity is a vector. So and concentration in mass transfer. Similarly, instead of using here Newton's law of viscosity, you will be using Fourier law of heat conduction. In mass transfer, you will be using Fick's law of diffusion. Then boundary conditions also. There are different boundary conditions in momentum transfer, different boundary condition in heat transfer, and different boundary condition in mass transfer. This is just a generalized case. So we'll come back to this generalized case once we solve our first problem in this shell balance approach. One by one, we'll discuss this again. How we have used this step one by one. How we have selected the first we will use, and then maybe at the end of the solving first problem, again we'll come back to the generalized method, and we'll try to understand the generalized method in detail actually, how we have made the use of the generalized method. Okay, the generalized method is very, very important. So you can solve any problem to get velocity profile, temperature profile, and concentration profile. There will be some changes here and there. 10% changes will be there based on given condition, and accordingly you can get a velocity profile, temperature profile, and concentration profile. This is generalized method. Then boundary condition. So what type of boundary condition you may come across? What type of boundary condition you may come across in momentum transfer? First type of boundary condition is no slip boundary condition. When I have solid fluid interface, no slip boundary condition. What it tells me that? It tells me that the velocity of fluid at the interface will be equal to velocity of solid. No slip boundary condition doesn't mean that velocity of fluid equals to 0. It means that velocity of fluid at the interface of solid fluid interface will have velocity that will be equal to solid velocity. Okay, so whatever, if solid is steady, so velocity of the fluid will also be a 0 velocity. Okay, if velocity of solid is 0, the velocity of fluid will also be equal to 0. If solid is moving with a velocity 10 meter per second, so at the interface, first layer of the fluid is also moving with a velocity 10 meter per second. So that is no slip condition. So there is no slip. There is no slip between last layer of solid and first layer of the fluid. Similarly, this is called as a modified no slip boundary condition. Same thing is there. Liquid-liquid interface. This is called as a modified no slip boundary condition. Okay. So here there will be a continuity of velocity as well as fluxes also. So velocity of first layer of this fluid will be equal to velocity of last layer of another fluid at liquid-liquid interface. So liquid-liquid interface, say consider this is last layer of this liquid one and this is first layer of liquid one, both will be moving with same velocity. And so whatever be the momentum flux in last layer of liquid, this liquid one will be equal to first layer of liquid 2. So that is also, there will be a continuity of velocity and flux. Okay, there will be continuity of velocity and flux at liquid-liquid interface. That is no slip boundary condition. And liquid gas interface, it is taken to be a zero flux condition. Zero flux condition because the liquid viscosity of liquid is much higher than viscosity of gases. So if I have interface, liquid gas interface, the liquid velocity viscosity is very high. Viscosity, I am telling, viscosity, viscous forces. The viscosity of liquid are very high as compared to gases. So they are not able to give any momentum flux in gases. Okay, because viscosity of gas phase is zero. So at this interface, we will be taking the boundary condition zero flux condition. There is no flux transported from liquid to gases because gases viscosity are negligible or gas is not able to give any momentum to liquid at this gas liquid interface. So gas phase is not able to give any flux, any momentum flux to a liquid, or liquid is not able to give any momentum flux to gases because of there is a huge difference in viscosity of liquid and gases. Okay, liquid and gases. So these are the types of boundary condition which is available in momentum transfer. Okay, first is no slip boundary condition, then liquid-liquid interface, modified no slip boundary condition. So there will be continuity of velocity and continuity of velocity and continuity of fluxes, and add liquid gas interface because the viscosities are quite different between liquid and gases. There will be a zero flux condition at gas liquid interface. So these are the three types of boundary condition. So with this input, okay, this is generalized method. So we can start our first problem. Take down this first problem. Now you write this first problem as it is. Okay, take down this first problem in your note. Okay, and then step by step we'll solve the problem. Take down the first problem, write this problem and draw the figure in your notes. Write a problem and draw the figure in your notes. Just let me know when you have completed writing this problem and drawing the figure. Write a problem and draw the figure. It is very important because you need to take out all the information given in a problem first of all. That will be first step. Take out all the information given in a problem. Consider a flow of liquid down an inclined flat plate of length L and width W as shown in figure. So this is inclined plate. This is inclined plate, you can see. So lower line, this line and this line, it is showing an inclined plate, and this is the reservoir. This is the reservoir. The inclination angle of the plate is beta. This inclination angle with a vertical direction of gravity is beta, and thickness of the film over a plate is delta. So this thickness is delta. This thickness is delta, and this is kept constant. This thickness is kept constant by continuously supplying the liquid from in the reservoir. If delta is very small as compared to length and W, this delta is smaller. Delta is smaller as compared to length and W. Okay, as compared to length and W. Derive the equation of for velocity profile and momentum flux profile, and hence develop the equation for maximum velocity. Once you get this velocity profile, you can get all these: maximum velocity, average velocity, mass flow rate, drag force on a plate. Given that viscosity and density of liquid is assumed to be constant, is given that viscosity and density of liquid is assumed to be constant, neglect all end effect because of the disturbances. So certainly I want to study fully developed flow. So neglect all end effects. Where will be end effects? In this area. Okay, in this area there will be end effects. Starting area there will be end effects. In this last area there will be end effects. So you can consider this will be entrance length and this will be exit length. So this will be generally less than you can say 1% of the total length of the plate. So this entrance disturbances, this is called as the entrance disturbances. End effect, this is called as exit disturbances. Okay, entrance disturbances, exit disturbances. So you can neglect these disturbances, and we are interested in fully developed flow. Okay, we are interested in fully developed flow. So because here, so direction of velocity, you can have multiple direction of velocity. Here also there is a forces, these molecules is forcing uh, some other forces also, because there is no plate at all. So I am not interested in this region, I am not interested in this region, I am interested in this fully developed flow. So fully developed flow, so derive the profile equation, velocity profile equation. Everybody has taken down this equation, this data. So you can write S in chat box if you have taken down this problem. Note down this problem and draw a figure. Read a problem carefully and take out all the information. So read problem carefully and take out all the information. Yeah, roll number 1, Abhinav.
Yes, sir.
So what is your conclusion? Just whatever be the given data, take out all the information, whatever information you can get from the given problem. It is just converting the English into engineering. So all the information is given in English. Now convert that into engineering information.
So maximum information is given in the figure itself.
Okay.
One information is that the film thickness is kept constant, that is delta,
Okay.
and delta is very small as compared to L and W.
Uh-huh.
And the rest is given in the figure itself. And all end effects are neglected.
Somewhere it is given steady state. So this problem is for steady state. Write down somewhere. This problem is for steady state. We are not solving it for a transient zone. Okay, steady state problem. So what are the boundary condition? Expected boundary condition. Roll number 17.
Yes, sir.
Yeah. What are the boundary conditions for this?
Sir, we have 3 boundary conditions, sir.
What are these 3 boundary conditions?
In the previous slide, we have discussed about solid fluid boundary.
No. Okay. These are the 3 types of boundary condition. So
Yes,
whatever
sir.
we have discussed here, these are the 3 types of boundary condition you will come across.
Yes, sir.
So what are the boundary condition given for this problem?
Sir, for this problem, we have liquid coming in, sir.
Okay.
And
So these are the 3 types of boundary condition.
yes, sir.
So what are the boundary conditions available for this problem?
Sir, for this liquid and
Here roll number 35, Praneeth. Roll number 35, Praneeth.
Hello?
Yeah.
Hello?
Yeah, tell me.
Sir, like this is the case for liquid gas, liquid solid.
Okay. So where is the boundary condition? What are the boundary condition I will take?
No slip condition.
So where?
Like a liquid film and a solid. Since solid is not moving, we can say the layer which is in
So
contact with.
this layer at this layer. So
Yes,
this
sir.
is the solid plate and this is the
Yes.
liquid plate. So at this interface, velocity is equals to, what is the velocity equals to at this interface?
So like flux would be zero at liquid gas film interface, sir. And here also velocity will be zero according to no slip.
According to no slip, what will be zero at this interface?
Velocity, sir.
Velocity will be equals to 0. So velocity equals to 0 at this interface.
Yes, sir.
So this is a solid plate and this is the liquid flowing over. What is another boundary condition you told?
Sir, for liquid gas.
So where is
Zero
that
flux
one?
at zero flux at liquid gas interface, sir.
Where is that liquid gas interface?
Like liquid and above liquid, it's gas only.
Yeah, very good. So this is the liquid and above this liquid there is a gas. So at this interface flux equals to 0. Okay, these are the two boundary condition. Anybody can think of any other boundary condition? Okay, viscosity is constant. How you can use this? viscosity is assumed to be constant. How to use this information? Viscosity is assumed to be constant. How this information is used? Roll number 61, Rutvik.
Yes, sir.
Yeah, viscosity is constant. Where and how this information will be used?
Sir, I think it can be used like throughout the liquid, the viscosity constant, like a liquid solid interface and a liquid air interface, means throughout the thickness of the film.
If viscosity is not constant, if viscosity is constant,
Yes, if viscosity is constant, so it is constant throughout the thickness of the liquid film.
yeah, that is what. So how to use this information? What is the consequences of constant viscosity? So if viscosity is constant, then only I can use which law?
If viscosity is constant, then I can use the Newton's law of viscosity.
That is what. If viscosity is not constant, then that is called as a power law.
Yes, sir.
Similar law, this law of viscosity is there. If viscosity is not constant, then it is called as a power law. Okay, that variation of viscosity is considered, and you have derived Newton's law of viscosity for that. That is called as a power law. Here, if viscosity is constant, so I can use Newton's law of viscosity. Indirectly, it is given that use Newton's law of viscosity for correlating velocity and flux. Use Newton's law of viscosity. Now, density is constant. Here, this information will be used. Roll number 90, Priyank.
Yes, sir.
Yeah. Density is constant. How
So
to
it
use
can be
this
used in
information?
mass transfer and heat transfer.
Mass transfer and heat transfer.
So density is constant, so we can use mass transfer.
We can use mass transfer. What this mean?
Fix law of mass transfer.
Don't need fixed law here. We are considering momentum flux.
So density is constant, so it will be incompressible fluid.
Yeah, very good. So density is constant means it is compressible fluid. So you can use simplified form of Newton's law of viscosity. Only first bracket is important. Second bracket is not important. For second bracket, incompressible fluid, so second bracket equals to 0. That is the thing actually. This delta is very, very small. It is given delta is very, very small. How this information is used? Or where this information is used? Roll number 109, Sashank.
Yes, sir.
Delta is very, very small.
So the
So many
thickness is
people are
very
leaving
small
the
in
meeting
this.
actually. Sia, Pritesh,
Yes, sir.
many people are leaving the meeting. Then they will say that okay, we have submitted this, we were there, we could not this and that. So excuses. That time I will count this actually. People are not attending the class seriously. Sashank,
Yes, sir.
delta is very, very small.
Yeah, yes, sir. For in the thickness, we can use it in the thickness so that the volume time at the time of calculating volume we can neglect it.
Yeah. So somehow any other very important input, delta is smaller using this information. Roll number 6, Aksh.
Yes, sir.
Yeah. delta is very, very small.
Yes, sir.
How to use this information for solving the problem?
So delta is small, so sir, don't know, sir.
So if delta is smaller, then only I can neglect the acceleration in the falling film. Okay, because gravitational force is acting on this film. Okay, everything is because this flow is because of gravitation, and this flow is open flow. So one boundary is open to atmosphere. It is not closed flow. So this delta is small. Because of this only, I can neglect the acceleration. So there is a velocity in this direction parallel to plate. Okay, parallel to plate. There is a velocity in this direction, but this velocity is not increasing. Otherwise, you know, there is acceleration due to gravity, and this acceleration is countered by keeping this delta smaller. Okay, because you can see here velocity is 0. Here velocity is 0. Some viscous momentum is transported in this direction. Okay, slowly velocity is increasing, slowly velocity is increasing, and it is reaching to maximum. But if this delta is very, very large, this viscous forces is not penetrated throughout the length of the film. Thereafter, there will be a acceleration in plate direction. But if this thickness is very, very small, this viscous forces is enough. It is balancing acceleration due to gravity. These viscous forces are enough to balance acceleration due to gravity. But these viscous forces are not so strong enough to prevent the flow. Okay, so viscous forces, there is a balance of viscous forces and gravitational forces. So viscous forces are enough to balance to prevent the acceleration, and this is happening only when delta is very, very small. Is this clear to everybody? Is it clear? Delta is very small, hence we can neglect the acceleration. There is a balance of viscous forces and gravitational forces. So if thickness is very large, then certainly there will be acceleration in the fluid. Acceleration in x direction or whatever direction I will select, that will be there. Okay. So anybody else can take out any other information from this problem? Okay, then you read the problem carefully at least couple of times. Try to understand this problem. Try to read this problem, understand this problem, take out all the given data, whatever you are understanding up to your understanding. So we'll try to solve this problem in next class. Okay. So thank you very much for attending this class. I request everybody to read this problem at least couple of times and take out all the given data. You keep this habit. Whenever given a problem, take out all the information from the problem before starting solving this problem. That is what you need to do. Okay, before next class, you take out all the information and then slowly we'll solve this problem. Okay, this first problem is very, very important. So I'll go very slow in solving this first problem. Okay, very slow I will solving this first problem. So, but this first problem itself, if you understood properly, you can solve any problem in shell balance, in heat transfer, mass transfer as well. Okay, then see you in next class.
Excuse me, sir.
Yeah, tell me.
Sir, the thing you explained about no acceleration,
No acceleration.
Yeah, sir, that we are talking in between the layer, liquid films, right? Different layers of film.
Acceleration means, say here, say this velocity I'm talking about, parallel to plate. Can you look at my cursor?
Yes, sir.
So you say here velocity is 1 meter per second. Here also velocity will be 1 meter per second.
So, sir, we have to find maximum velocity, average velocity. It
Yeah,
would be constant, right?
that is a gradient of velocity is there in perpendicular to plate.
Okay, sir.
Okay, gradient of velocity will be there perpendicular to plate, because here velocity is 0, here you have some velocity.
Yes, sir.
As I am moving away from the plate, velocity will increase. But if I am moving parallel to plate in a beta direction, gravity, and this flow is under the influence of gravity, and this flow is open flow. On one direction there is a gas open to atmosphere. So if you throw say a drop of water from the top, certainly the velocity, if you are throwing, say if you are on a building, okay, 10 floor building, and you are throwing water from top, so velocity of all the drops will increase as it goes down towards the ground. That is because of acceleration due to gravity. Okay, gravitational force. And here delta is smaller, so that molecules are experiencing viscous forces also. And this some molecules are in touch with the solid plate. So they are experiencing viscous forces, and these gravitational forces is supporting the flow, and these viscous forces is opposing the flow. So it is the balance. It is the balance in such a way that acceleration is negligible. No acceleration. But viscous forces are not so high that there is no flow at all. If say viscosity is very, very high, this is very high viscous fluid, then what will happen? So, and say this inclination angle beta is close to 90, and viscosity is very high, so you will have no flow condition. Okay, there will not be any flow, but that viscosity is not that much high, so delta is not that much small to prevent the flow, but it is not that very high to have accelerating fluid. If say thickness is very, very high, so certainly there will be acceleration in the fluid actually as I move parallel to plate.
Yes, sir.